Good afternoon, ladies and gentlemen. Good morning for the people in North America. Welcome to this webinar. My name is Stijn Daniels. I'm the president of ICTCT and talking to you from nearby Brussels, Belgium. I will be your host today on behalf of the steering committee of ICTCT, and a special welcome to our speaker of the day, that is Professor Gary Davis of the University of Minnesota in Minneapolis, USA. Before we start the webinar, just a few short announcements. For those who did not do yet and who don't know ICTCT yet, the International Collaboration on Theories and Concepts in Traffic Safety, please visit our website and register to stay informed about our activities. And the next main activity will be our conference that still will be held online next month. Will be hosted by the people from the German Aerospace Center, the 28th and the 29th of October. The registration site is open now, and what is important and probably relevant for many of the people attending the session today is that we will have a special session on surrogate safety measures during that conference. So please register and be welcome to actively participate to the conference. I also take the occasion to promote our next planned webinar that will be on the 3rd of December this year, same time, same day, Friday. And the guest of that day will be Claes Tingvoll, who is the retired Director of Traffic Safety of the Swedish Transport Administration, and as such, one of the founding fathers of the Vision Zero concept that became well known worldwide. So certainly worth the effort to listen to what Mr. Tingvoll will be presenting the 3rd of December. Okay, the webinar of today, the speaker of today, Gary Davis, is a professor at the University of Minnesota. He holds a chair in transportation, got bachelor degrees in philosophy and psychology from Eastern Washington University, and master's and PhD degrees in transportation engineering from the University of Washington. His research interests, I will be very short about that, include lots of things, but among others, causal inference and impact assessment in traffic safety, and also the application of Bayesian statistical methods in traffic and transportation engineering. His contribution today is entitled Graphical Models, Surrogate Endpoints, and Crash Modification Factors, which is a title that is at the same time promising and a little mysterious. So we are really looking forward to the presentation. Just before we start, very practically, we foresee to have a lecture of about a presentation of about 40 minutes, followed by a Q&A session of around 20 minutes. If you have questions, please ask them, put them already during the session in the chat using the Q&A button that you can see on your screen, below the screen, somewhere in the middle, it should be, and send it through already. We will bundle the questions then after the session and pass them on directly to Gary Davis. Just one final remark before we start. The session will be recorded and will be made available afterwards through the ICTCT website. Good. I would say time now to go over to the actual webinar. So, Mr. Davis, Gary, the floor is yours.
All right. Thank you, Stijn. Let me see if I can share my screen. Oh, you got to stop sharing yours, I guess, first. Oh, okay.
I did,
Now
yes.
Okay, I understand. Okay, so we got that far. Okay, I think we got it. So let me go to the first page. So I changed the title slightly. I've got the word surrogate outcomes instead of surrogate endpoints, just to connect with other usage that I've done when doing this work. Outcome and endpoint seems to be used as more or less synonyms, so the meaning hasn't changed very much here. So let me just dive right into it. So I'm going to start with a sidetrack on evidence-based medicine. And probably most of you have heard of this or encountered this before. Let me just give a fairly common definition of what's meant by that. Evidence-based medicine is a conscientious, explicit, and judicious use of current best evidence in making decisions about the care of individual patients. And going along with this idea of evidence-based medicine is a hierarchy of the quality of evidence from different sorts of research activities. And at the top of the list here is randomized controlled trials. And then second best are observational studies, such as case control studies. And then down here in third best are evidence that might come from expert opinion or physiological mechanisms. And you'll notice that evidence from mechanisms gets a fairly low rank here in this evidence-based medicine hierarchy. And that's usually justified by citing cases where treatments that were based on mechanism type reasoning were found to be ineffective when they were evaluated with the randomized controlled trials. And kind of one of the poster childs is this use of drugs to control cardiac arrhythmia, which was supposed to reduce heart attacks, but actually didn't. And another study looking at the way surgery to kind of clean out the loose bodies and stuff in your knees didn't really seem to have much effect, okay, when it was evaluated with a trial. So that's kind of the rationale for putting mechanism-based thinking and mechanism-based evidence down at a lower rank compared to the empirical studies, the controlled trials, and the observational work. And when we go to road safety, we see something similar, I think, or one can argue anyway, that we've gone through something similar in road safety, at least over here in North America. And if you go to the design guides that we use here in North America, what you'll find is mechanism-based arguments for making decisions such as how a radius for a circular curve or the length of a vertical curve. And in particular, looking at the lengths of vertical curves, the standard design guide says the length of the vertical curve should be such that a driver can see far enough ahead so that he or she can come to a stop before hitting an obstacle in the road. Back about 1988, okay, which is kind of my last year in graduate school, Ezra Hauer wrote a paper. And Professor Hauer pointed out that, well, one thing, these existing guidelines didn't give you very much or gave you no guidance at all, in fact, on the safety consequences of different sorts of design decisions. So if I lengthen or shorten a vertical curve, what effect will that have on crash occurrence? Well, there was nothing out there to allow you to make that sort of assessment. And he also pointed out that there really wasn't much empirical support for a lot of these design practices anyway, at least as far as their effectiveness as safety measures. And maybe the poster child for this particular conclusion was that when researchers actually took a look to see if there was a relationship between, say, vertical curve length and crash risk, they weren't able to find any correlation here. So this is something similar, okay, to what happened in medicine at roughly the same time. Okay, this idea that we've got mechanism-based reasoning for making decisions, the evidence supporting this mechanism-based reasoning as far as its safety impacts is fairly weak, okay, or non-existent. And again, at least over here in North America, since about 1990, there's been a general shift in the sorts of evidence that's used to support safety-related decisions to recommendations based on observational empirical research, which would be roughly evidence-based medicine level 2 type studies. We don't often do level 1 type randomized controlled trials, but the general drift away from this total reliance on mechanism-based reasoning to evidence based on actual empirical research at the observational level, all right, has been fairly steady over the past 20 years and resulted, among other things, this publication of the Highway Safety Manual back in the year 2010. And the second edition of which is, if it isn't out now, it's soon to come out. So you might ask, what possible good are mechanisms or thinking about mechanisms in roadway safety? Well, kind of switching back to medicine now as our parallel sort of area that we're looking at, there still is an ongoing debate about the relative importance of mechanism type thinking versus empirical research in medicine. And let me just read a quote. If we want to get into trying to explain why a particular treatment works, Robin Bloom, taking a quote from a paper she wrote, understanding the effects that various clinical and demographic factors have on treatment outcomes requires us to develop more, quote, lovely, unquote, explanations. And this is where knowledge of mechanisms come in. Essentially, what Professor Bloom is saying is that we might have a randomized controlled trial. It was performed on a particular population. The medical practitioner has to make decisions about whether a particular patient is close enough to that population for those findings to apply or not. And when one is faced with that, some understanding about the mechanisms by which the treatment works can be and sometimes is helpful. A second issue that comes up is this idea of surrogate outcomes. And a surrogate outcome is something I can observe that, well, for instance, if I have a medical treatment and the outcome of interest is preventing death, and we perform a randomized controlled trial. All right, well, strictly speaking, we ought to wait and see how many patients die, all right, before assessing the treatment. If we can find an outcome, okay, that allows us to determine whether the treatment's working or not without having to wait for people to die, that's a definitely good thing. And that's what's meant by a surrogate outcome. Again, there's an ongoing debate about what counts as a surrogate outcome or how to find one or how reliable they are. Prentice, back in 1989, gave some criteria. And the one I want to focus on here is this criteria 3. And Professor Prentice says that to be a good surrogate, the treatment and the true outcome should become conditionally independent given the surrogate. And this idea of conditional independence is something that I'm going to get a lot of mileage out of during this talk here. And then finally, a related issue is this idea of external validity, or at least in the road safety business, what we call transferability. And I'm going to not read the quotes, but the basic idea here is that when I want to start talking about whether something that worked over here in, say, Minnesota is going to be applicable to Florida or Sweden, some understanding about the mechanism by which that road treatment works was certainly helpful and arguably necessary to determine whether we can transfer that knowledge from one place to some other place here. So what I'm going to do is take a look at these three issues as they play out here in this road safety business. So the tools that I'm going to use are what Judea Pearl, professor of computer science and artificial intelligence at the University of California, Los Angeles. All right, what Professor Pearl calls graphical causal models. And a graphical causal model has two components, and one is a directed acyclic graph. And so here's my graph, little simple example graph. It has three nodes, X, V, and Y, and then it has arrows connecting these nodes. And the arrows basically code information about the dependencies of these nodes when these nodes represent random variables. So essentially what this little graph is saying is that the joint probability distribution of these three variables, X, V, and Y, all right, decomposes into a conditional distribution of Y given V. That's what's indicated by this arrow. The conditional distribution of V given X, that's what's indicated by this arrow. And then the unconditional distribution of X. And one of Professor Pearl's great contributions is to establish a relationship between the connectivity structure in the graph and conditional independence among the random variables that are represented by the nodes of the graph. And again, this is something we're going to spend a little bit more time on later on, okay, but it's a property that we're going to get some mileage out of here. So, explaining crash modification factors, that's what I'm going to take on first, developing and testing explanations. So first, let me talk a little bit about constructing explanations. And I'm going to blame this methodology, what I'm talking about here, to Charles Sanders Peirce, a philosopher, lived in the United States, the late 19th, early 20th century. Although most of us will probably recognize that the kind of reasoning that's going on here, all right, certainly wasn't unique to Professor Peirce. You see it cropping up over and over again, all right, throughout kind of the history of science, really. And Peirce calls this the method of hypothesis. And so here's the fact I want to explain, and that fact is I have a runny nose. I want to explain that. And so here's my proposed or hypothesized explanation that I have a cold. And why that counts as an explanation is that I've got a model, and that model says if you have a cold, then you have a runny nose. And then that plus my hypothesis that I have a cold logically implies the fact that I'm trying to explain, that I have a runny nose. So this makes this I have a cold a plausible explanation. It doesn't prove that I have a cold. If I were to claim that this proves it, I'd be committing a logical fallacy. All right, but it makes the explanation plausible, okay, this sort of connection. And Professor Peirce and pretty much anybody else would say, well, we certainly don't stop at this point. All right, what we do next is we start testing this explanation. And so we derive some other consequences from it. So for instance, if I have a cold, then I have a fever. And then I go look to see if I have a fever. And in this case, I don't have a fever. All right, so that brings our original explanation into question, and we might want to go start looking for a different explanation instead. And down here, I've got ... the ellipses, and that means that this process doesn't usually just terminate, okay, very quickly. It's an ongoing process, and we develop and refine our explanation with additional empirical research to provide constraints that we have to satisfy. And in some sense, this is, like I say, an ongoing scientific activity, this constructing of explanations. So let me illustrate this with trying to explain why what in the US anyway we call pedestrian hybrid beacons, which are pedestrian actuated traffic signals, okay, that can be installed at a marked crosswalk in order to hopefully stop vehicles and allow pedestrians to cross here when they're having trouble doing it. And let me also be explicit about what I mean by a crash modification factor at this point. And crash modification factor, we'll abbreviate that CMF. That's basically the expected crashes with some modification divided by the expected crashes without the modification that you would see if you performed a controlled experiment. So in some sense, it's a measure of the causal effect of the modification on the crash experience. And this idea that at least ideally it would come from a controlled experiment, all right, means that we're not talking about just any observed expected crashes with or without. All right, we're being in the situation where we've got enough control so that a correlation that we observe in a study can be plausibly attributed to a causal effect, okay, arising from that. So with pedestrian hybrid beacons, we actually have two, at least that I know of, what are called empirical based before-after studies, trying to estimate their crash modification factors. One of them done in the city of Tucson came up with an estimated CMF of 0.31. And then a later study that used data from several cities, including Tucson, and they came up with an estimated crash modification factor of 0.24. So we got at least some reasonably reliable evidence that the pedestrian hybrid beacons do reduce crashes, and we have some rough estimates of the magnitude of that reduction from these studies here. So the first thing is that I wouldn't try to explain a crash modification effect unless I was at least reasonably certain, all right, there was an actual effect out there trying to explain. And in this case here, I think that that condition is satisfied. And there's also been field observations. And one of the observations is that drivers don't like to yield to pedestrians at marked unsignalized crosswalks. And that when you install pedestrian hybrid beacons, that tends to increase the yielding rates. So here's our initial hypothesis about how pedestrian hybrid beacons work. And that is that the pedestrian crashes at marked crosswalks are caused by drivers failing to stop. And the PHBs reduce the crash frequency by increasing the stopping rate. All right, I'm going to say I don't know this is true. This is a hypothesis. And then we're going to check this hypothesis to see if it lives up to the evidence. So we need some sort of way of connecting our hypothesis to our outcomes of interest here. And so now what I'm going to do is I'm going to construct my graphical model. And I'm going to construct that by starting out with a structural equation that describes the crash events. So here's the sort of event we're talking about. Okay, we got a section of road. There's a vehicle traveling down that road. The vehicle's traveling at some speed. Okay, we'll give that speed a name. We'll call it V1. And a pedestrian attempts to cross that road here. And so the pedestrian travels this little distance D2. And then in this region here, the pedestrian's at risk for being struck by the vehicle. The driver of the vehicle may attempt to stop. So after a reaction time, the driver brakes, and then we have a collision if the vehicle arrives at this conflict zone while the pedestrian's in the conflict zone. And we don't have a collision if the pedestrian either gets through before the vehicle arrives or the vehicle arrives first. So kind of the simplest sort of scenario, okay, we can think of that describes pedestrian vehicle encounters. And that's going to be one of the components of our model, okay, that's going to explain or try to explain how these PHBs work. So here's my graphical model that I'm proposing to try to get a handle on this issue. And so down here, Y stands for my crash outcome. And this bottom layer here of the graphical model, all right, that's essentially that structural equation that I described a little bit earlier. We got the pedestrian speed, the distance the pedestrian travels, the vehicle's initial speed, the vehicle's distance, the driver's braking rate, the driver's reaction time, and they all feed into this variable Y, okay, which codes whether or not a crash occurs. And so in this model here, this simple model, all right, we're going to allow for two types of driver. Okay, there's the drivers that brake, which means after a reaction time, the driver attempts to stop. And then the non-braking drivers, which just continue at their initial speed. And we'll let pi1 stand for the fraction of braking drivers. And then we're going to have two types of pedestrian. All right, we're going to have careful pedestrians, and a careful pedestrian only moves into the street if the vehicle is at least the AASHTO stopping distance away from the collision point. Right, so we've got a speed limit, we can compute a stopping distance, and the pedestrian only selects to cross the road when the vehicle is at least that far away. And then the not careful pedestrians basically enter the road independent of where the vehicle happens to be. And so we'll let pi2 stand for the fraction of careful pedestrians. And so here's our pedestrian hybrid beacon up here. And the question is, does it affect the fraction of careful peds? How does it affect the fraction of careful drivers? All right, that's the hypothesis that we want to try to get a handle on. So set up the model for a particular road with a particular distribution of speeds and a particular distribution of reaction times and braking rates for the driver, distribution of speeds for the pedestrians, and run a Monte Carlo simulation and simulate crash probabilities as functions of the fractions of careful pedestrians and braking drivers. And so one of the things we see is that if all, make sure I get this right here, if all pedestrians are careful, pi2 equals 1.0, and the effect of the pedestrian hybrid beacon is to change the fraction of braking drivers from 0 to 80%, all right, then essentially without the pedestrian hybrid beacon, here's our simulated crash probability. With the hybrid beacon, here's our simulated crash probability. And the crash modification factor associated with that simulated outcome, about 0.204, sorry. And that's roughly consistent with what's been reported in the empirical Bayes EV studies. So that is a candidate explanation for the effect of the hybrid beacon, that all pedestrians are careful and that it increases the the fraction of drivers that brake, and that gives us our PHP here. All right, but on the other hand, if I assume that 80% of the drivers attempt to brake, and the effect of the hybrid beacon is to change the fraction of careful pedestrians from 0 to 100%, then I get a crash modification factor about 0.33 in my simulated world. And that also is roughly consistent with what the empirical work has shown. So just knowing the estimated crash modification factors for the PHBs is not sufficient to hone in on a plausible explanation for how the PHB works. We need some more data to add additional constraints to what we've got going on here. So what we did was take a look at the distribution of pedestrian injury severities in the Twin Cities. And let me just focus over here on situations where the vehicle is going straight and the speed limit is 30 or 35 miles per hour on these roads. And this is roughly consistent with what I was simulating in our simulation model. And under those conditions, what we find is that about 51% of the reported injuries were in this possible range, either no injury, a property damage only type situation, or no injury reported here. About 47%, there was evidence that pedestrian was injured, either hauled to the hospital or at least injured and taken to the hospital by someone else. And then at about 1.5%, there was a fatality here. So whatever we're saying about the operation of these vehicle pedestrian encounters, all right, that model also ought to reproduce injury severities like this as well. And so we're going to use this injury severity data as an additional constraint. So if I take the distribution of injury severities as data, and I think about the fractions of careful pedestrians and the fraction of braking drivers as parameters, all right, I can think about trying to estimate these fractions using maximum likelihood. And what I've kind of depicted here is kind of what that likelihood function would look like. And we want to find the fraction of braking drivers, the fraction of careful pedestrians that maximizes this, the logarithm of the likelihood function here. And what I found was that if I assume 98% of the drivers brake, and that the fraction of careful pedestrians ranges from about 0 to a little less than 40%, I'm along this ridge in my likelihood function. And if I change my fraction of braking drivers, then I get log likelihoods that are lower than what I get here on my ridge. And if I move outside this roughly 40% boundary, then I start to get log likelihoods that are less here. So as far as the injury severity data go, the evidence suggests that we ought to assume that almost all drivers attempt to brake when faced with a encounter with a pedestrian, and that the fraction of careful pedestrians ranges somewhere between about 0 and 40%. All right, for my model to reproduce the injury severities, okay, that I have reported here. Okay, so here's my second hypothesis, okay, about how the pedestrian hybrid beacons affect pedestrian crash risk. And that hypothesis is, first of all, that almost drivers attempt to brake. 98.98 is my fraction of braking drivers. And what the pedestrian hybrid beacon does is it changes the fraction of careful pedestrians from roughly 0 to 40% without the hybrid beacon to 80 to 90% with the hybrid beacon. And so that puts me in this region over here where my simulated crash modification factors are consistent with, again, what's been reported, all right, in the empirical days before after studies here. So that set of hypotheses, most drivers attempt to brake. The hybrid beacon works primarily by increasing the fraction of careful pedestrians. That explains both my distribution of injury severities and my observed crash modification factors for the pedestrian hybrid beacon. Okay, is this the final word? I'm sorry, certainly not. Okay, additional testing is required. All right, this thing makes a fairly strong claim that if I were to go out and watch pedestrians in the field, what I should be seeing is a fair number of not very careful pedestrians when there's no pedestrian hybrid beacon. And when the pedestrian hybrid beacon gets installed, then I ought to see that most of the pedestrians are acting in a careful manner. All right, this isn't the final word. We should go out and do this sort of empirical research to test the hypothesis and proceed to develop and refine the model here. But this is the sort of process, as far as I can tell, all right, that one would need to go through if one wanted to construct, okay, a detailed explanation of how a particular safety-related modification works. In other words, from our empirical work that we do now, we can determine whether it works or not. Unfortunately, the empirical work doesn't tell us how it works. Okay, if we want to start untangling how it works, this is the kind of work I think that we would need to do. So with that controversial claim floating in the air, let me check my time here, 35, and kind of accelerate a little bit. And pick on the two other topics that I want to at least touch on here. One of them having to do with surrogate outcomes. So before I get into the surrogate outcomes, let me go back and talk about this idea of de-separation in graphical models. That's Professor Judea Pearl's connection between the connectivity in a graphical model and conditional independence. And so I've got two little graphical models here. All right, in this one here, all right, this node V, all right, what you can see is it basically blocks the path between X and Y. And so since V blocks that path, all right, then we could say that in the associated probability distribution, V or X and Y are conditionally independent given V, or equivalently that V de-separates X and Y. So we have this graphical criteria here that V blocks this path. And from that, if this is graphical models, a good representation of the process, we can infer, all right, this conditional independence condition. When I go over to this graph on side B, again, V blocks this path here between X and Y, but now we've got a second path between X and Y. So when we're looking at this stuff, we don't worry about directed versus undirected paths. All paths count. And in this path here, this node V is what's called a collider node or an inverted fork, which means it's got, when a traveler's path, I get an arrow going into V on this length and also an arrow going into V in this length here. Unfortunately, with collider nodes, if I observe V, then what that does is it disrupts an independence condition that existed already here. So that while V blocks this first path here, V does not block this path here. All right, the node U though does block that path. And so even though V doesn't de-separate X and Y, we can say that the pair V and U does de-separate V and Y. And so that X and Y are conditionally independent given both U and V taken together here. So what can we do with that? All right, well, Ellie actually recommended that I stay away from equations if possible, okay? So I keep the number of equations down to a minimum. I've got basically 3 slides that have equations on them, and then this is the second one here. But this is the result I want to get at, okay, when we start talking about surrogate estimation. And that is, suppose I've got, okay, so now suppose I've gone through my explanation construction activity, and I've put together a graphical model that I've got good evidence actually explains how a crash modification effect works. Okay. And so in this graphical model, the node X stands for the either absence or presence of a safety-related modification. The node Y stands for either the non-occurrence or the occurrence of a crash. And then V stands for a subset of the nodes. And then P of E stands for the probability distribution of that. So here's the result I want to suggest. And that is that if X is a root node, that means it doesn't have any arrows going into it. And this set V de-separates X from Y, then we can come up with a formula for estimating crash modification factors based on observations of V. And essentially that formula here says that the estimated crash modification factor, it's the ratio of V in the modified condition divided by the density of V in the unmodified condition. and then weighted by the distribution of V in crashes occurring in the unmodified condition. All right, and then the integral of that. Okay, so what's that mean? All right, that means that arguably that this set of nodes V that d-separate X from Y are behaving quite plausibly like crash surrogates, okay, in the sense that they seem to be associated with the crash outcome. They respond to the modification. And given this set V, all right, the modification and the crash outcome are conditionally independent. Okay, so there's Prentice's three conditions. And if V does satisfy those conditions, then it turns out we can write out this formula that would tell us how to estimate a crash modification factor without waiting for crash occurrence. All right, what we would need though is a sample of crashes in the unmodified condition that we can estimate this distribution of my surrogates from here. Okay, and this result, I'll cite a paper here at the end. Okay, if you want to see our argument in favor of it, you can find it in the paper here. What I want to do next is just simply do a simulation study to show that this actually is a plausible result. And so we go back to our model of the way pedestrian hybrid beacons work and take a look at this graphical model. And what I can see first is here's pedestrian hybrid beacon, and the way we're assuming it works is it affects the fraction of careful pedestrians. And here's a path from pedestrian hybrid beacon down to the crash outcome. And we can see that whether or not a pedestrian is careful, that blocks that path. And so we've got D-separation. We can argue that a careful ped, all right, D-separates the hybrid beacon from the crash outcome. But if we take a look at this, there's a couple more paths, pedestrian hybrid beacon, down to whether or not a gap is accepted. And then over here, the initial distance of the vehicle, and then down to crash here. That's a second path. And then there's actually a third path. Down to acceptance, distance, speed, and then down to crash. So there's three paths here. Fortunately, careful ped blocks all three of those paths. And so that would be one surrogate outcome that we could think about for this situation. All right, what that says is that if this graphical model is plausible, actually describes what's going on, then observing the effect of the hybrid beacon on the whether pedestrians are careful or not would be sufficient to determine whether it has a significant safety effect. Okay. On the other hand, it's kind of hard to tell whether a pedestrian's careful or not. You might need to know something of what's going on in his or her mind, but it is a lot easier to observe whether a gap gets accepted or not. Unfortunately, if I observe gap accept here, all right, that also blocks this path, but accept is a collider node on this path here. So if I want to block this path here, I've got to get another observation over here, initial distance. And initial distance also blocks this path here. So the set, accept, and initial distance of the vehicle also de-separates PHV from crash. And so those would be another set of plausible surrogate outcomes that we could consider here. If we could determine the effect of the hybrid beacon on pedestrians' gap acceptance and the initial distances of the vehicles when they're accepted, all right, that would be another way to come up with an alternative estimate of the crash modification factor. And so what I ran here was another Monte Carlo simulation just to illustrate that this works the way it's supposed to. And so in this situation, again, we got 98% braking drivers. And we're assuming here that the way the hybrid beacon works is to change the fraction of careful pedestrians from 30% to 80%. And earlier, we did a simulation of the CMF associated with that particular change. That came out to be about 0.36. And so to implement this kind of a surrogate-based estimation of crash modification factors, I need to know distributions of deseparating variables in the population of crashes. So I simulate a set of crashes and the fraction of careful pedestrians in crashes when there's no PHV turns out to be only 3%. And I go to my formula and I specialize it to this particular case. It turns out to be fairly simple in this particular case. And I get my surrogate-based estimate of crash modification factor of 0.36, which was pretty much the same as I got from the brute force Monte Carlo simulation a little bit earlier. And then if I go and treat accept and vehicle initial distance as my surrogate outcomes, and go through the derivation of applying that alternative formula, yeah, lo and behold, I again get 0.36, all right, as my estimated crash modification factor. All right, so what are we saying here? What we're saying is if we have a, if we have a graphical model and we don't need to know the details of the distributions of the variables in the graphical model, all we need to know is the graphical structure. That graphical structure will tell us how to identify surrogate outcomes, and that it also tells us what sort of data we need to collect in order to estimate a crash modification effect using the surrogate outcomes. Okay, so let me jump finally to my last topic. We're starting to run short on time, and that's transferability of crash modification factors. And so in this slide here, okay, I say a lot about transferability, transportability, external validity, blah, blah, blah. All right, here's the issue that we're interested here in Minnesota. And that is basically when you go to the highway safety manual, okay, the tools in the highway safety manual are essentially statistical summaries of the vehicle and driver mixes that have been present in mostly North America during the past 30 years. All right, that vehicle and driver mix is expected to change as automated vehicles hit the road. And the question we're interested in is, can we take the substantial research that went into the original highway safety manual, for instance, and adapt it to an environment where we have automated vehicles going on here? And essentially the approach we're using is, again, work done by Judea Pearl and his graduate students called transportability analysis. And essentially, the key tool here in this transportability stuff is a selection diagram. And a selection diagram is just a graphical model where we've added an additional node that describes how situations differ from each other. So in this case here, my modification works along this path, whereas the situation differences work along this path here, and then they feed into my crash outcome, all right, down here. All right, well, doing kind of the same trick that we use to get that surrogate estimate of crash modification factor for graphical models that have a structure like this, where the modification works along one path, whereas the situation differences work along another path. All right, you can actually derive, kind of using that same trick, you can derive a formula, all right, that says that the crash modification factor in the new situation, that's equal to the crash modification factor in the old situation times this kind of complicated looking calibration factor. To do the calibration factor, again, what do we need? Well, we need these surrogate outcomes, V, and now V is being a surrogate for the situational differences. All right, the surrogate outcome in V in the new situation, the old situation, and then the distribution of crashes in the old situation when the modification was present. Similar stuff here when the modification is absent. All right, if you have data on these 1, 2, 3, 4 different probability distributions, all right, you can, at least in principle, go through the arithmetic, estimate this calibration factor, and then convert the old CMF to a new CMF here. All right, that's the claim. And so let me do describe another little simulation experiment looking at the plausibility of this. So here's my pedestrian hybrid beacon graphical model again. And now I've added a selection node here. And basically the selection node takes on the value 0 when we've got no automated vehicles, and 1 when we have 50% of the population out there is automated vehicles. And the automated vehicles we're simulating, all right, always brake for pedestrians. And when they brake, they have an average reaction time of 1/2 second and an average braking rate of 0.8 Gs. So they're faster and brake harder, okay, than human drivers generally do. All right, so the situation we simulated here was a situation where 100% of the drivers attempt to brake. The PHB operates by changing the fraction of careful pedestrians from 20% to 80%. All right, well, the crash modification factor of installing in our simulated world, okay, the crash modification factor for installing a pedestrian hybrid beacon when the AVs are present comes out to be 0.258 that we get by just directly simulating. When we apply our recalibration formula, we take the old CMF and multiply it by that calibration term, we get 0.257, which is what we would expect to see here. There's little difference between the crash modification factor in the old and new situation. And that's because in this particular example here, the pedestrian hybrid beacon is essentially protecting the pedestrians from human drivers. The automated vehicles are able to stop soon enough so that they almost always avoid collisions with pedestrians in our simulated world. All right, so the effect of the pedestrian hybrid beacon is to protect the pedestrians from the human drivers. And essentially the CMF then, all right, that we would get in these two situations comes out to be about the same. Although in the simulated world, all right, the crash probability with the automated vehicles is about 1/2, all right, of what it was with the nothing but human drivers. So basically, essentially what is happening in the simulated world is that the automated vehicles are always avoiding collisions. So about 1/2 of the collisions are taken off the table. And then the effect of the pedestrian hybrid beacon is protect pedestrians from the other 1/2 of the situation, all right, where we encounter the human drivers. All right, but the argument here is that at least in principle, if I've got a graphical model that I've got confidence in, that would allow me to identify some surrogates that if I had data on them, would allow me to at least plausibly transfer a CMF estimated in the current conditions where all the vehicles are human to a situation where we have a significant fraction of automated vehicles here. Okay, so in summary, what have we done? All right, well, we've looked at Pearl's graphical causal models, and we're claiming that they offer schema for representing mechanisms that connect modifications to crash experience. We can use these graphical causal models to pose and test hypotheses that try to explain how CMFs work. If we had a plausible graphical model, we could use that to identify surrogate outcomes and compute a surrogate estimate of a crash modification factor. And if we had a plausible graphical causal model, we could assess transferability of CMFs to new environments and recalibrate existing CMFs, all right, when this transfer is justified. So let me offer thanks to the two students, Jingru Gao and Christopher Chong, that worked on this, to the Roadway Safety Institute, which provided some funding to chase after these ideas. On this slide here, this talk is based on 2 papers and a report that are all published. Here's how you would find these darn things. And then finally, let me say thank you, and time permitting, I'd be glad to take any questions.
Thank you very much, Gary. And I think the first question that I saw is already answered. That was a reference to one or another paper, and that is the thing that you just come to provide. And I'm looking to the chat box whether there are questions from the audience. I guess it was that clear.
Either that or that terrifying.
So maybe one question. So you did a kind of a calibration by checking whether the simulated CMFs were equal to the ones that have been found in the literature. Is just the fact that they correlate enough to say that this is a valid surrogate safety measure?
So our argument for a surrogate, for something to be a surrogate safety measure is, first of all, we have to have the graphical model that explains how the modification works. Okay. All right. If you're willing to assume that this graphical model is a correct description, then a deseparating set is a valid surrogate. Yeah, that's just a mathematical fact, but it's a mathematical fact of the assumption that, yeah, this graphical model is an accurate description of what's going on. All right, so if you are willing to accept that, you're willing to accept the graphical model, then that deseparation criteria. So I can go to the graphical model, I can determine nodes that deseparate, and if that's a set of deseparating nodes, then that tells me that if I had data on the distribution of those deseparating nodes, I could compute a crash modification factor. And I think most would agree that that counts as a valid surrogate. If I can take those surrogate measures and estimate the safety related effect of an intervention, that sounds like a pretty good surrogate to me. All right, so the validity of the surrogate follows mathematically from the assumption that this graphical model accurately represents the situation. Coming up with that graphical model, that's another question. Okay, we talked a little bit about what you'd have to do to go through to do that in the first part of the talk. But once you get to that graphical model, all right, the validity of the surrogate is a mathematical fact.
Yeah, indeed. Okay, thank you. Another question, when you talk about gap acceptance at crosswalks, do you mean gaps between pedestrians or between cars?
Boy, I should have made that more clear. Yeah, it's the gaps in the vehicle traffic that the pedestrians are accepting here. And so probably something we all know, all right, that if people are indifferent to accepting gaps, then they might get run over. If they're careful about accepting gaps, then they don't get run over. And so, yeah, we're talking about how the pedestrians choose gaps in the traffic stream, okay, in order to get across.
Okay, thank you. And then the next one, why did you assume that beacons affect pedestrian behavior and not drivers?
Well, initially we assumed that it affected the drivers. That was our initial hypothesis. And so we started out assuming that it affected drivers. All right, that assumption wasn't sufficient to explain, well, it could explain the crash modification effect of the beacons, but also the assumption that the hybrid beacons affect the pedestrians and not the drivers also could possibly explain the crash modification factor. So we had to make a choice. All right, so we got the severity data, and the severity data in order to reproduce our distribution of injury severities. All right, we had to conclude that the hybrid beacons affect primarily the pedestrians and not the drivers. In other words, to get the severity distributions, we had to assume that almost all drivers try to brake when confronted with a imminent collision with a pedestrian. So it wasn't, we started out assuming that they affected the drivers, assuming that doesn't explain the injury distribution. And so those two empirical constraints, the estimated CMS and the injury distribution, is what led us to that second hypothesis.
Okay, thank you. I see there are currently no other questions, but looking at the time, I see it's exactly 4 p.m. here in Central Europe. So I think we can conclude the session by saying thanks to Gary for his interesting presentation, and thanks to the audience for attending, for listening, and asking questions. So thank you all, and see you back at one of our future activities. Thank you.
All right, thank you.